Bella Anais, and I'm going to be teaching you how to draw Bohr's orbital diagram and Lewis dot diagram. And so this presentation is called Bohr's orbital and Lewis dot diagrams. And so on the slide, I put two images. The one on the left shows shows Bohr's orbital model for aluminum, and the one on the right shows Lewis dot diagram for water. And I just wanted to give you a little sneak peek of how those two diagrams look like, but we'll get into how they look like later. So we're going to begin with Bohr's orbital diagram first. So before we get into how the diagram looks and how to draw it, we first want to know who discovered it, well, who came up with the diagram. So who is Bohr? Niels Bohr was a Danish physicist born on October 7th, 1885. Bohr came up with many theories and models like Bohr's atomic model and Bohr's orbital model, which we are going to be looking at today. And so what is Bohr's orbital diagram? So Bohr's orbital diagram displays the arrangement of all electrons that an element or atom contains. And so the way to draw it is you would put the number of protons and neutrons in the nucleus in the center. So it would be like a little circle, and you would put the number of protons and neutrons that an element contains. And so around the nucleus are going to be orbitals, and that's where you're going to be displaying the electrons that an element has. And the amount of electrons that an element contains determines the number of orbitals. And so in parentheses I put H, which is hydrogen, has 1 electron, which equals 1 orbital. And so I want to clear up some confusion that may come with this information. Just because an element might have 5 electrons, it doesn't mean it's going to have 5 orbitals. Or if an element has 20 electrons, it doesn't mean it's going to have 20 orbitals. And I'll get into the amount of electrons that are in these orbitals, so the distribution of electrons. But I want to clear that up, that number of electrons is not the number of orbitals that will be displayed in the diagram, if that makes sense. So orbitals are energy levels, and they vary in the amount of energy. So the closest orbital to the nucleus, which is called the core, has the lowest energy, while the outermost orbital, which is called the valence orbital, has the highest energy. And so electrons can move orbitals. In order for an electron to move orbitals, it either has to release or gain energy. And so they can they either receive or release energy as light. And so an electron that gains energy gets excited and moves to a higher energy level, and an electron releases energy and it moves down to a lower energy level. So I provided 2 images, and the one with the little dots, the colored dots, purple and blue, we kind of see the ground state, which is just the nucleus and just 1 orbital with 1 electron. And we see how it gets excited and the electron moves to a higher energy level. And we also see in the second image it's with absorption and emission. We see how when the electron absorbs energy, it moves to the 3rd energy level, but when it released energy or emitted energy, it moved back down to the 1st orbital. And so that's how they move. You have to gain or release the energy. So here we have Bohr's orbital diagram for the neutral atom aluminum. So aluminum has 13 protons and 14 neutrons in the nucleus. And we see here the 13p and 14n in the middle in a blue circle, and that represents the nucleus, and it's in the center. It has to be in the center. And since this is a neutral atom, the number of protons and electrons have to be the same. So we're going to have 13 electrons in 3 orbitals around the nucleus. And so here we have 3 circles around the nucleus, and they have different amounts of electrons. And I'll get into that later, but here it is. We have 2 electrons in the first orbital, we have 8 in the second orbital, and we have 3 in the third orbital, all totaling up to 13 electrons. So rules of distribution. So different orbitals can only hold a certain amount of electrons. So the first orbital can only hold 2 electrons. The first orbital is the closest to the nucleus. And the second orbital and third one can hold only 8 electrons. And when we start filling these orbitals with electrons, we first need to fill the first orbital. So the first orbital needs to have 2 electrons before we move on to the second orbital. And electrons need to be separated before making a pair of 2. And I know this might be confusing, but I'll explain it later in my examples. But basically, what I'm saying is we need to have separate for, I'm talking specifically for the orbitals 2, 3, and above. You first want to give the electron space, so put a first electron, 1 electron, and then 2, and then 3, and then 4, and then if you have more, then you put the electron next to another electron, and that will make more sense in my example. But I just wanted to make that clear that they first need to be separated first before you make a pair of 2 or put them together. I know that doesn't make sense, but it'll make sense in my example. And so here's Bohr's orbital diagram for a neutral atom boron. And so here we see that boron has 5 protons, 6 neutrons, and 5 electrons. So it's a neutral atom because there's the same amount of protons and electrons, so it's a neutral atom. And here we see that it has the number of protons and neutrons in the nucleus. I'm so sorry, it's my brother. We have the number of protons and neutrons in the nucleus in the center, and it has the right number of orbitals with the right amount of electrons in each orbital, and the electrons are separated. And it kind of makes sense here in the image because they're not close together. In the second orbital, there's one on the top and then one on the side and one on the bottom, so they're not close together, they're separated. I'm going to be showing you 2 examples of Bohr's orbital diagram for neutral atoms. The first one will be lithium and the second will be nitrogen. So we're going to begin our first example of Bohr's orbital diagram, and we're going to be starting off with a neutral atom. So here we have lithium, and lithium has 3 protons, 4 neutrons, and 3 electrons, and the number of protons and electrons have to be the same in order for it to be a neutral atom. And so the first thing we want to do is write the number of protons and neutrons in the nucleus, which is in the center. So we're going to put 3p and for protons and 4n for neutrons, and here we're doing a circle representing the nucleus, which is in the middle. And we realize we have 3 electrons, and so we're going to distribute these electrons in the orbitals, and the first orbital can fit only 2 electrons. So we're going to draw the first orbital, which is around the nucleus, and we're going to draw 2 electrons. And the electrons are going to be across from each other. They're not going to be next to each other. They always have to be across, not next to each other. So we're going to put 1 on the top and 1 in the bottom, across from each other. And so we're going to do the second orbital, and the second orbital we're just going to put we're just going to put 1 electron to complete the 3 electrons, to have a total of 3 electrons. And the second orbital can fit up to 8 electrons, only 8. But we only need 1 to complete the 3, like I said. So we're just going to draw that one on the top, aligned with the one in the bottom. And so now we have the nucleus with 3 protons, 4 neutrons, and the 3 electrons distributed in 2 orbitals for lithium. For our second example of Bohr's orbital diagram, we have another neutral atom, and this neutral atom is nitrogen. And so we have nitrogen, and nitrogen has 7 protons, 7 neutrons, and 7 electrons. And so the number of protons and electrons are the same because it is a neutral atom, like I previously stated. And so the first thing we're going to do is write the number of protons and neutrons in the nucleus, which is in the center. So 7p for 7 protons, 7n for neutrons, and a circle representing the nucleus. And so we have 7 electrons, and we're going to distribute these electrons in 2 orbitals. And so the first orbital can only fit 2 electrons. So we're going to draw the first orbital around the nucleus. And like I said, the first orbital can only hold 2 electrons. So we're just going to draw the 2 electrons across from each other. And so there are the 2 electrons. And so we realize that we have 5 electrons we need to draw. So we need a second orbital, and the second orbital can hold only 8 electrons. So but instead of drawing all 8, we can just draw all 5 to complete the 7 electrons. So we draw the second orbital around the first orbital, and here we are going to draw the 5 electrons. And so we're going to draw the 5 electrons in the second orbital. And so this is what I mean by separating electrons. We want to draw them not next to each other. We don't want to do that. We first want to separate them in each corner. So like you can just imagine 4 corners, and we need to first draw them in 4 corners before we draw them together. And so here I'm going to show you in the back how to correctly draw it. And so that's what I was talking about in the beginning of the presentation, how we need to like separate electrons. So here we're going to draw it all over again. The first orbital and the second orbital. So the 2 electrons in the first orbital. And so this time we're going to separate the electrons. So we put 1 right there, the second one in the other corner, the third in the third corner, and the fourth in the fourth corner. So that's kind of like separating them in a way. And so now that we realize we still need 1 more electron, we can fill it and put it next to that electron, so making like a pair of electrons. So you can now draw them together, but we first need to draw them out in their own corner before doing a pair. And so this is Bohr's orbital diagram for a neutral atom, nitrogen. So we have 7 protons, 7 neutrons, and 7 electrons distributed in 2 orbitals. So an ion is an electrically charged atom due to either gaining or losing electrons. So an atom might gain or lose electrons in order to be stable and complete the octet rule. And the octet rule is basically stating that in order for an atom to be stable, it needs to have 8 total electrons in the valence orbital. And hydrogen has an exception to the octet rule because oxygen hydrogen applies to the duet rule, and the duet rule states that an atom is stable if it has 2 electrons in the valence orbital. And so the electrons in the valence orbital are just called valence electrons. So it's like more simple. When we get to ions and we look at the valence orbital, if the valence orbital has 5 through 7 valence electrons, it can gain electrons in order to complete the octet rule. But if the valence orbital is less than 5 valence electrons, then it will have to lose those electrons present in the valence orbital, because it will take more energy to gain electrons than to lose them. And so there's 2 types of ions. A cation is a positive ion. So in a cation, an atom loses its valence electrons because it cannot gain electrons to complete the octet rule. And since it's losing the electrons, there's more protons, which makes a positive charge. And the second type of ion is an anion, and it is a negative ion. And this is where an atom gains the needed electrons in order to complete the octet rule. And so since you are gaining electrons, there's going to be more electrons than protons, which means there's going to be a negative charge. In the structure of an ion, we're going to have the diagram in these brackets, and you're going to be putting the charge, whether positive or negative, and you're going to be putting that outside of the bracket on the right corner, and you're going to put it with the quantity, so like a positive 2 charge or negative 5 charge on the right corner. Here I'm going to be showing you 2 examples, one of a cation and one of an anion, and I'm going to be showing them now. To be looking at a cation, and the cation is basically a positive charge, and so we're looking at carbon. Carbon has 6 protons, 6 neutrons, and 6 electrons, and this makes a neutral atom. So this is carbon's neutral atom. So this is Bohr's orbital diagram for the neutral atom of carbon. And so we're going to be drawing carbon's ion. And so everything's going to stay the same. We're going to put the 6N and 6P in the middle. Everything's going to be the same. So you're just going to put 6P and 6N in the center, in the nucleus. And then we're going to draw the first orbital the same. And so if we look at the second orbital is called the valence orbital. And the electrons in the valence orbital you can just call them valence electrons. So we have the valence orbital, which is the last outermost orbital. And here we have 4 electrons, aka 4 valence electrons. And so we see that if less than 5 valence electrons, we will lose all those electrons. So we're going to be losing those 4 electrons in the valence orbital, because it would take more energy to gain electrons than to lose them. So we're just going to lose all 4 of them completely. And so for the ion, we're just going to put, for the ion, we're just going to put the first orbital with the 2 electrons, because we lost all 4 of them completely to complete the octet rule. And basically the octet rule is stating that in order for an atom to be stable, we need to have 8 valence electrons in the outermost orbital. And so we just lost them. We can either gain or lose electrons to complete the octet rule, and in this situation we lost the electrons. And so for the ion model, you have to put a diagram in brackets. And so now we don't have 6 electrons, we have 2 since we lost 4. And so now we have a charge of positive 4. So it's a cation because it has a positive charge of 4. and it gets its charge because there's more protons now. There's 6 protons and there's 2 electrons, so there's more protons than electrons, which makes a positive charge. And so in the outside of the bracket, not inside, in the right corner, we're going to write the charge. So we're going to put 4 plus outside of the bracket, and this basically represents the charge, the positive charge. And so here we have carbon's ion, which is a cation. So we're going to be looking at a anion. A anion is basically a negative charge, which is the opposite of a cation. And today we're looking at oxygen. Oxygen has 8 protons, 8 neutrons, and 8 electrons, and that is a neutral atom. And to the left, we have Bohr's orbital diagram for the neutral atom oxygen. And so we're going to be drawing oxygen's anion, but before that, we're going to be looking at oxygen's valence orbital. And so the rule is if the outermost orbital, which is the valence orbital, has 5 through 7 valence electrons, it will gain electrons in order to complete the octet rule. And if it has less than 5, it will lose those electrons. But in this case, we are going to be gaining 2 more electrons to complete the octet rule. I have the 8 protons and 8 neutrons in the nucleus. And so we're going to draw the first orbital and the second orbital. Also, that's my brother. I'm so sorry. So we're going to put the 2 electrons in the first orbital. And we're going to be drawing the electrons in the second orbital. And first we have to separate them. And now that we separated them, we're going to draw them in pairs. So we're going to draw them in pairs now. And we're going to fill the valence orbital with 8 electrons to complete the octet rule. So now our valence orbital is completely full with 8 electrons. Draw our brackets around Bohr's orbital diagram. Sorry if it's a little bit messy, but we're going to draw the brackets and we're going to write the charge. And since we gained 2 electrons, there's not going to be 8 electrons. There's now going to be a total of 10 electrons. And so now we notice that there's more electrons than protons. And we know that electrons are negative and protons are positive. So now we have a negative charge since there's more electrons. And so since we gained 2 electrons, we have a negative charge of 2. And we're going to write that in the outside of the brackets in the right corner. And so this is an ion of oxygen. So now we're going to be looking at ionic compounds. And ionic compounds are 2 or more oppositely charged ions that are held together by electrostatic forces of attraction. So these ionic compounds are just 2 or more ions, but they have to be opposite ions. So it has to be cation and ion together. It can't be cation and cation because positive charges don't attract each other. It has to be positive and negative to form these compounds. And so here I have 2 examples of ionic compounds, and we have beryllium oxide and boron nitride. And so I'm going to display the video. So we're going to be looking at ionic compounds, and ionic compounds are oppositely charged ions held together by electrostatic forces of attraction. So cations are going to be pulled together with anions because they are oppositely charged. So here we have beryllium, and here we have beryllium's neutral atom, and here we have oxygen and oxygen's neutral atom, and they are both Bohr's orbital diagram. And so here we have beryllium's ion, and here we see that it has a positive 2 charge because it lost those 2 valence electrons in the outermost orbital in order to complete the octet rule. and here we have it in brackets. And here we have oxygen's ion, and here it has a charge of -2 because it gained 2 electrons in order to complete the octet rule. So it has a negative charge of 2, and we have that in brackets as well to show that it's an ion. And so we are going to create a compound between these two, between beryllium and oxygen, to show that they are compounds. No, to create compounds. And basically, we're just going to write these two ions and just place them next to each other to create ionic compounds. And that's how you basically create ionic compounds. You just put the ions close to each other. So here I am drawing the ion, a beryllium's ion, right here. So I'm just drawing beryllium's ion right here. And I'm going to draw oxygen's ion next to beryllium's ion to form an ionic compound. Oxygen's ion. And we're writing the charge as well. And so these two attract each other because they have oppositely charged ions. So beryllium has a positive charge of 2 and oxygen has a negative charge of 2. And so here we have, this is an ionic compound between beryllium and oxygen. So this is an ionic compound, and this ionic compound is called beryllium oxide because we are combining beryllium and oxygen together since they are oppositely charged ions, not atoms, ions. So for our second example of ionic compounds, we're looking at boron and nitrogen. So here we have boron's neutral atom. We have nitrogen's neutral atom. And here we have boron's ion, and it has a charge of +2 or +2. And we got +2 by getting rid of the valence electrons in order to complete the octet rule. And here we have nitrogen's ion, which has a charge of -3, and it got a charge of -3 because it gained 3 electrons in order to complete the octet rule. And so we are going to create an ionic compound between boron's ion and nitrogen's ion. And they are going to create an ionic compound because they are oppositely charged ions. And they have different quantities, but that's okay. As long as they're different charges, it's really what matters. Here we are drawing boron's ion, nitrogen's ion. So we're just gonna put the charge, and that's basically it for drawing the combination, the ionic compounds. And from this we get boron nitride. And I know I spelled it wrong, but in the end I correct it. It ends with an E at the end. And so now that we know how to draw Bohr's orbital diagram, we are now going to look at Lewis dot diagram. And so before we begin to learn how to draw Lewis dot diagram, we want to know more about the scientist. So who is Lewis? So Gilbert Newton Lewis was an American physical chemist. He was born on October 25th, 1875, and he is well known for his creation of the Lewis dot diagram. What is Lewis dot diagram? So Lewis dot diagram displays the arrangement of valence electrons that an element has. So before we were looking at all the electrons, but now we are looking at the valence electrons, so the electrons in the outermost orbital. So what we're going to do is put the chemical symbol in the middle, and this is just for just one element. So for example, carbon, if we were just doing carbon alone, it would just be C in the middle because C is the chemical symbol for carbon, so we'd put C. and then we would put the valence electrons around the symbol. So carbon has 4 valence electrons, so we would put 4 valence electrons around the chemical symbol C, and only 8 valence electrons can surround each symbol, with aka completing the octet rule. And valence electrons will be represented by dots. So if we were doing carbon, for example, we would put C, and then we would put 4 valence electrons surrounding it. So we could put 2 on the top and 2 on the side, or we could put 2 on the top or 2 on the other side. It doesn't matter. But that's just for a single one. If we're doing bonds, which I'll later show an example, then it would be different. Well, not completely different, but the process would be a little bit longer. And so 2 notes that I have here is valence electrons are electrons located in the outermost orbital, which I've probably said a bunch of times. And another note is valence electrons are responsible for holding 2 or more electrons in chemical bonds. And so you might be wondering how many valence electrons in an element. And so I provided you with an image on this slide. And basically, these elements are in columns. So the first column, the second column, and so on. And so these elements in these columns all have one thing in common, and it is the number of valence electrons. So the first column we see hydrogen, H, and in the bottom we see Li, which is lithium, and so on. So that first column has all those elements have 1 valence electron. The column next to it, beryllium, Be, and all those other elements on the bottom of beryllium have 2 valence electrons, and so on. The 7 steps for drawing Lewis dot diagram. So the first step would be to find the total number of valence electrons. And so to get a better understanding of the steps, we're going to be doing the example phosphorus chlorine 3, and the 3 is for chlorine, just chlorine alone. So we know phosphorus has 5 valence electrons, and we know chlorine has 7 valence electrons. But since we have 3 atoms of chlorine, we're going to multiply 7 by 3, and we're going to get 21 out of that. So we're going to add 21 and 5 from phosphorus, and we're going to get a total of 26 valence electrons. And step 2 would be to find the least electronegative atom and put it in the center. So fluorine is the most negative atom, so whichever element that is furthest away from fluorine would be in the center. So as we can see, phosphorus is furthest away from fluorine, so phosphorus would go in the middle. We would have P in the center, and then we would just have 3 atoms of chlorine around phosphorus, as we have it right there. And again, hydrogen has an exception to this rule, to this step, because hydrogen only has 1 electron, which means it can only make 1 bond, so it can't be in the center. So step number 3 would be to put 2 electrons between the chemical symbols to make a bond. And in the image, you see how there are 2 electrons between each symbol. So 2 electrons in the top, 2 electrons on each side, both left and right, to connect the different chemical symbols. And these are bonding, which electrons are bonding, then they're going to be represented by a dash. So 1 dash represents 2 electrons. And so later we'll change that, but just for now, you should know that a dash represents 2 electrons, and non-bonding electrons are just regular dots. Step 4 is to draw the skeleton structure. So for the skeleton structure, we already completed step 5 and 6 with the skeleton structure, but basically the structure is just the dots, and we in the structure we don't put the dashed lines, it's just pure dots. So for step number 5 is to complete the octet rule for each atom on the outside. So we already did it here. We see each chlorine atom has a total of 8 valence electrons. So if you see in the image, each chlorine has one on the left side, on the right side, and the top and the bottom for each chlorine atom. And you're just putting the remaining electrons in the outside. Only the first, you first put the electrons on the outside symbols, not the center one. That you could, if you have remaining ones, then you put it in the center. But you first need to put the electrons on the outer symbols. And so that brings us to step number 6, place remaining electrons on the center atom. And so since we had a remaining of 2 electrons, we put it on the bottom of phosphorus. And we completed the octet rule already. And so step number 7 is to draw the structural formula. And all we changed was the bonding electrons by representing that by a dash. So that's all the steps. And so now we're going to be doing 3 examples of Lewis dot diagram for neutral atoms. So I'm going to roll the clip. So we are going to be doing Lewis dot diagram for 3 neutral atoms. So the 3 neutral atoms we have is carbon, hydrogen, and neon. And we're first gonna begin with carbon. And so we're gonna begin with carbon. And carbon has a total of 4 valence electrons. And since this is just a single element, we're going to put the chemical symbol C in the center. So it goes in the center. And we're going to distribute these 4 valence electrons around the chemical symbol. And what you want to do is imagine a box around the chemical symbol, like how I'm doing right now, just like putting an outline. So you want to put them like in little, like pretend it's a box, basically. And so we're going to distribute these 4 electrons around the chemical symbol in a box shaped form. And just like that. And so that is Lewis dot diagram for the single atom carbon. And if we had more electrons, we would distribute them and put them next to the existing electrons. But since we just have 4, we're just going to leave it like that. And remember, you want to separate the electrons and not put them in a pair unless you have more electrons. And so now we're doing hydrogen. And hydrogen just has 1 valence electron. And so we're going to put the chemical symbol H in the center. And we're just going to draw just 1 valence electron on the side. And it doesn't matter however way you draw it, just as long as it, it makes sense. There's not like any gaps. And so now we're going to do neon. And neon has 8 valence electrons. And so we're going to put the chemical symbol Ne in the middle. And just how we did for carbon, like a box-shaped form, we're going to do that for neon. We're going to distribute these 8 valence electrons around neon. And so see how I'm first doing it, separating the electrons. And now we have 4 left, remaining electrons. So we're going to create a pair now. Just how we did for Bohr's orbital diagram. And we're going to do that all around to complete the octet rule, since neon has 8 valence electrons. And that is Lewis dot diagram for a single atom of neon. And so now we have 3 examples of Lewis dot diagram. And so now we're going to be doing two examples of a Lewis dot diagram for a cation and a anion. And we are going to be doing a cation first, and we are going to be working with the element sodium. And sodium has one valence electron. So one valence electron. And what we're first going to do is put the chemical symbol of sodium, which is Na, in the center. So Na in the center. And we're going to draw the one valence electron around the symbol, so right there. And since it only has one valence electron, we're going to lose that valence electron to complete the octet rule, because it would take more energy for it to gain 7 more valence electrons to complete the octet rule, instead of just losing that one valence electron. So we're going to get rid of that valence electron, and we're just going to put Na in parentheses, well, in brackets basically. And so it is positive because we are losing that electron, so there's going to be more protons than electrons, creating a positive charge of 1. And so that is sodium's ion in a Lewis dot diagram form. And so now we're going to be doing an anion, and we're going to be doing the element chlorine. And chlorine has 7 valence electrons. And like we did in the example above, we're going to put chlorine's chemical symbol in the center. And we're going to put the 7 valence electrons around the chemical symbol. And like I said before, we're going to separate the valence electrons before we start filling them in pairs. So now we're going to be filling them in pairs. And so it has 7 valence electrons, which means it's going to gain 1 valence electron in order to complete the octet rule. And so we're going to gain that 1 valence electron. And we're going to put the chemical symbol in the middle. And we're going to draw all 8 electrons around chlorine, because it gained that 1 electron. And so it gained that 1 electron. And now we have 8 total valence electrons. And so we're going to put it in brackets. And so since it gained 1 valence electron, it's going to have a negative charge of 1, since there's more electrons than protons. And I put plus by accident, but I changed that. So it's negative. It has a negative charge of 1. And here are two examples of Lewis dot diagram for a cation and a anion. So we're going to be doing a Lewis dot diagram for ionic compounds. And we are going to be working with calcium oxide. And so the first thing we want to do is draw the chemical symbol for calcium in the center. And calcium has 2 valence electrons, which we are going to draw around the chemical symbol. And next we're going to draw oxygen. And we're going to put oxygen's chemical symbol in the middle. And oxygen has 6 valence electrons. So we're going to put the chemical symbol in the middle. and draw those 6 valence electrons around calcium. And before we make a pair, we always have to separate them in the 4 corners and then make a pair like we did right now. And so we notice how it needs 2 valence electrons to complete the octet rule. And so calcium is going to transfer these 2 electrons to oxygen in order to have oxygen complete the octet rule. And so we're going to redraw this. So calcium, it's going to have no longer have any electrons because it gave them to oxygen. So it lost 2 valence electrons, so it's going to have a positive 2 charge. And oxygen will gain these 2 valence electrons to complete the octet rule. And here we're going to draw a total of 8 valence electrons around the chemical symbol oxygen. And since it gained 2 valence electrons, it's going to have a negative charge of 2. And so this is an ionic compound, calcium oxide. So for our second example of Lewis dot diagram for ionic compounds, we have H3N. So ionic compounds for H3N. And so the first thing we're gonna do is write the chemical symbol for hydrogen, which is H. So, and we have 3 atoms of hydrogen, so we're gonna write 3 H's because there's 3, and the number 3 only applies to hydrogen and not to nitrogen. And we know that hydrogen has 1 valence electron, so we're just gonna draw 1 valence electron next to the chemical symbol for each symbol. There we go, so 3 on each H. And next we're going to draw nitrogen's chemical symbol, and we know that nitrogen has a total of 5 valence electrons. And so we're going to draw the chemical symbol for nitrogen, and we're going to draw the valence electrons around nitrogen. And since hydrogen doesn't have enough electrons to gain electrons to complete the octet rule, it is going to lose that 1 valence electron. But nitrogen has 5 valence electrons, which means it can gain electrons to complete the octet rule. And so these 3 valence electrons from these 3 atoms of hydrogen are going to be transferred to nitrogen in order for nitrogen to complete the octet rule. So it is going to be, so hydrogen is going to give its electrons to nitrogen. And here we're going to redraw it again. Nitrogen with the complete octet rule. Octet. And we're going to put it in brackets. And since it gained 3 electrons, it is going to have a negative charge of 3 because it gained these 3 electrons. And hydrogen is going to have a positive charge of 1 since it gave its electron to nitrogen. So these 3 hydrogen atoms are going to have a positive charge of 1. And so now we're going to combine these the diagrams, and we're going to put nitrogen in the middle because remember, hydrogen has an exception to the second step, which is putting the least electronegative symbol in the middle. So nitrogen is going to be in the middle, and hydrogen is going to be on the outside. So here we have nitrogen, and we're going to have these 3 hydrogens diagrams around nitrogen's diagram. So here we have 1, And here we have another, and we're going to put one on the top. And so this is an ionic compound for H3N. And that is it. So we are going to be doing a Lewis dot diagram for the chemical formula H2O, and this is for a single bond. So we have water, aka H2O, and so we know that hydrogen has one valence electron, and we have two atoms of hydrogen. So we're going to multiply that one valence electron to those two hydrogen atoms, and we're going to get a total of 2 valence electrons. And this is step 1 of drawing Lewis dot diagram. And we have oxygen, and we know that oxygen has a total of 6 valence electrons. And so we're going to add up the 6 and the 2 to get the whole total of valence electrons. And so we're going to get a total of 8 valence electrons. And so now we're going to combine hydrogen and oxygen, but we're going to put oxygen in the center, and that is step number 2, putting the least electronegative chemical symbol in the middle. And remember, hydrogen has an exception and cannot be in the center because it only has one electron, which means it can only make one bond. And so now we're going to combine these elements with 2 electrons, which is step number 3. And so yes, they are bonding, which we're going to put a dash to represent the bonding electrons, but we're going to do that later. And so now we have left over 4 electrons to draw around, and we cannot draw them around hydrogen because hydrogen cannot, and it cannot complete the octet rule because it follows the duet rule, which means having only 2 valence electrons, which it already has. So we're gonna have to draw those remaining 4 valence electrons around the center atom, oxygen. And so that is the skeleton formula. And so now we're going to represent these bonding electrons with a dash, and we're going to do that in the structural formula. And so here we are basically just putting a dash between these elements because they are bonding, and we're just going to just draw the non-bonding electrons as we have already on the top. And so that is the structural formula. And so we see we only have one bond between these elements. We just have one bond creating one chemical formula. And so that is it. That is the Lewis dot diagram for water. And so now we're going to be doing a Lewis dot diagram for a double bond. And here we have oxygen 2 or O2. And we know oxygen has 6 valence electrons. And since we have 2 oxygen atoms, we're going to multiply the 6 valence electrons to 2. And we're going to get a total number of 12 valence electrons that we're going to be drawing in the dot diagram. And so we're going to put the 2 chemical symbols side by side. So we're going to have O next to O. And step number 2 is to put 2 electrons in the middle to create a bond. And so these 2 electrons are bonding, and later on we're going to substitute that with a dash. But first we're going to do the skeleton structure. And so we're going to have to distribute these 12 valence electrons to the symbols, and we subtract the 2 because we already drew 2 electrons, so we have a total of 10 electrons left to draw. And so here we are drawing them around the chemical symbol to the right. And so we already completed the octet for that symbol, so now we're going to move on to the next one since we have a remaining of 4 electrons to draw. And so here we drew the remaining 4, and as you can see, the chemical symbol to the right has a complete octet, but the one to the left does not. It needs 2 more electrons to complete the octet, to have a complete octet. So what we're going to do is we're going to take these 2 electrons from the bottom, and we're going to put them in the middle to make a double bond, so that both chemical symbols have a complete octet. And so here we are redrawing it again. But this time, instead of having 2 electrons in the middle, we're going to have 4. So we have a double bond. And so now both chemical symbols have a complete octet. So each atom has 8 valence electrons now. And so that is the skeleton structure. And we're going to be drawing the structural formula in a second. I'm so sorry, that's my brother. And so here we're going to just substitute those 4 valence electrons with 2 dashes. Since 1 dash equals 2 valence electrons, we're going to have 2 to represent 4 valence electrons. And we're just going to draw the regular non-bonding electrons around each chemical symbol. And here it is. That's the structural formula. And so that is a double bond. And that is a Lewis dot diagram. So for our last example for the Lewis dot diagram, we're going to be doing a triple bond. And here we have N2, or nitrogen 2. And we know that nitrogen has 5 valence electrons. And since we have 2 atoms of nitrogen, we're going to multiply 5 times 2 to get a total of valence electrons. And that is step number 1 of drawing the Lewis dot diagram, getting the total number of electrons. And so now we're going to draw the chemical symbols N. So we're going to put N and N side by side. And step number 2 is to put 2 electrons to create a bond. And so here we are putting 2 electrons to make a bond. And so later we're going to replace it with dash, but for now we're doing the skeleton structure. And so we're going to subtract 10 with 2 because we already drew 2 electrons, and we're going to have 8 electrons to draw. So we're starting with the right. We are drawing 6 valence electrons. And as you can see, the right atom already has a complete octet. And here we're going to put the remaining electrons. And as I said before, the one on the right has a complete octet while the one on the left does not. So we're going to get these 2 electrons in the bottom and put them in the middle to have a complete octet on the left, but that's still not going to be enough. So we're going to take these 2 electrons on the side and put it in the center and making a triple bond. And so now both atoms have a complete octet. And so when creating these bonds, we are having these 2 atoms share these electrons. So right now, these 2 nitrogen atoms are sharing a total of 6 valence electrons. And so we're just going to draw the non-bonding electrons on the top. and that is the skeleton structure for N2. And the total number of bonds that we can have is 3. So after this, we would not be able to create bonds. And so now we're going to draw the structural formula. So instead of having 6 dots, we're going to have just 3 dashes. 3 dashes, yeah, representing the electrons being shared between these two atoms. And that is the structural formula for N2. And so that is a triple bond that we created, and that is Lewis dot diagram for N2. So the difference between Bohr's orbital diagram and Lewis dot diagram is that Bohr's diagram is like displaying all the electrons that an element has, while Lewis dot diagram is looking at just the valence electrons, so the electrons in the outer orbital. And so another difference is that the Lewis dot diagram creates bonds. So it is creating bonds between different atoms, while Bohr's orbital diagram is just showing showing the electrons that an element has. And in Bohr's orbital diagram, it displays the nucleus and it has orbitals, while the Lewis dot diagram just has the chemical symbols. And so those are just 4 differences that I found, and that is it for my presentation. I know it was a little bit long, like so long, but that is it for my presentation.